mighty Himalayas stands a temple of education, an institution that shapes young minds of today into ambitious, conscientious, and dauntless individuals. Individuals who will become leaders of tomorrow. This is Jaypee University of Information Technologies, Solan, where education meets excellence. Conceived as the joint vision of the Government of Himachal Pradesh and the founder chairman of Jaypee Group, Shri Jaiprakash Gaur, JUIT Solan is the first private university of Himachal Pradesh established in 2002. Over the last 2 decades, JUIT Solan has been relentlessly pursuing its mission of contributing to a better world by cultivating creativity and advancing fundamental knowledge through education among students. Adorning the picturesque slopes of Waknaghat hills in the Solan district of Himachal Pradesh, the university campus spread across 25 acres provides a peaceful and serene setting in the lap of nature for young minds to hone their skills for a brighter future. JUIT offers undergraduate, postgraduate, and doctoral programs in various fields of study to include computer science and engineering, information technology, electronics and communication engineering, biotechnology, bioinformatics, civil engineering, and management.
JUIT has been producing polished graduates who are working as experts in various fields in country and abroad. More than 200 alumni have become acclaimed professionals in countries like Canada, America, and also Europe.
As Dean Academics and Research, I have had the privilege of witnessing a remarkable journey here. We aim to provide an educational opportunity to one and all, irrespective of their background. In JUIT, our main aim is to produce industry-ready professionals and good human beings. From the beginning, our institution has been known for its research and innovation, and now it emphasizes on interdisciplinary research and collaborative work. We are also aligning with the principles of NEP 2020, and following NEP, we are preparing the students to excel in their professional journey. We have been continuously ranked in NAC and NIRF. Now we are also ranked in international rankings such as the Times Higher Education ranking and QS ranking.
We regularly upgrade the IT infrastructure at our university. Recently, we have added a good number of new machines in various labs.
With modern hostels for both boys and girls, faculty residences, a healthy and hygienic students' mess, auditorium, sports facilities, and other amenities. The university campus makes life vibrant and enjoyable for students, both inside and outside the classroom.
Handling 1900 students in the age group of 17 to 23 years is challenging. In JUIT, we create a conducive ecosystem for a student to develop and nurture his or her personality besides the academic curriculum. Providing excellent amenities in the hostels, good nutritious food, active sports fields, vibrant and diverse co-curricular activities clubs, NCC, etc. are all domains which fall in my responsibility as the Dean of Student Welfare.
The university exposes its students to placement teams from several well-known companies, and the students here in this university do get placements in the organizations like Microsoft and Amazon.
JUIT Solan stands tall as an institution committed to academic excellence, holistic development, and industry relevance. With its focus on research and innovation, as JUIT graduates step into the professional world, they carry with them not only knowledge but also the skills, values, and perspectives necessary to make a positive impact on society.
So, hello and good morning, everyone. Welcome to the last session of the Geotechnical webinar series that is conducted by IGS Shimla chapter and JUIT Waknaghat. So, first of all, I'd like to congratulate you all for a very healthy appearance here, and you have participated well in the last 4 sessions very actively, including the students from the student chapters as well, the faculty members from various places, and also the esteemed member of the IGS. So with this, I'll first of all like to welcome our speaker for the day, Dr. Rohan Deshmukh, who is the Geotechnical Solution Engineer in Bentley Systems India. Welcome, Dr. Deshmukh.
Hi, sir. Welcome. Good morning to everyone. I hope I'm audible.
Yes, sir. You are perfectly audible.
Okay.
So, shall we start with the proceedings for today?
Sure.
Okay.
Just to give me a moment. Yeah, you can.
Let me introduce you first.
Yep.
All right. So, welcome to everyone. So, let me give a little introduction about Dr. Rohan Deshmukh. So, Dr. Deshmukh is Geotechnical Solution Engineer in Bentley Systems India Private Limited. He has completed his BTech in Civil Engineering from Dr. Babasaheb Ambedkar Technological University and has secured Lunar Gold Medal from there. He has done his ME in Geotechnical Engineering from Matusri College of Engineering and Research in Nashik, and then he joined his PhD in Geotechnical Engineering from Sardar Vallabhbhai National Institute of Technology, where he also secured the Best Thesis Award from ICRIP for his PhD thesis entitled Field and Numerical Evaluation of Geosynthetic Reinforced Flexible Pavement. He served as Assistant Professor in Civil Engineering Department, MGM College of Engineering, and Tanna College of Engineering in Navi Mumbai. He also served as Senior Technical Engineer in McAfee Environmental Solutions Private Limited, and he was the Trainee Geotechnical Engineer in Fugro Geotech Private Limited. Dr. Rohan has more than 20 publications in international journals, book chapters, and conferences of repute, and has various research awards to his name. He is also the reviewer of various reputed journals such as International Journal of Environmental Research, Journal of Civil Construction and Environmental Engineering, International Journal of Pavement Research and Technology, Studia Geotechnica et Mechanica, etc. Dr. Rohan is actively working in taking challenging assignments in geotechnical engineering, in construction, design of foundation, offshore geotechniques, geosynthetic testing, geosynthetic reinforced soil structure, pavement geotechniques, ground improvement, soil investigation, soil stabilization, and such other related researches as well. Moreover, he has also taken up various software and field testing based assignments related to geotechnical and highway engineering. So with this introduction, I'd like to thank Dr. Deshmukh to derive some precious time of his to come on the IGS Shimla chapter, and will hand over the stage to him to present his lecture, please.
So first of all, thank you, Neeraj, for giving me this opportunity. I also would like to thank Jaypee University and the IGS Shimla chapter for inviting me as a speaker for this session. And I welcome all the participants. So just give me a moment. I'm sharing my screen. I hope my screen is visible to everyone. So myself, Rohan Deshmukh. Currently, I'm working as a geotechnical solution engineer in the Bentley Systems.
Sorry,
so
as of
yeah.
now, your screen is not visible.
Okay. Entire screen share. Yeah, I hope now it is. Now fine?
Yes, now it is visible. Thank you.
Okay. Thank you, Neeraj. So I'm currently working as a geotechnical solution engineer in the Bentley system. So my role here in Bentley is to educate the people regarding our geotechnical portfolio or the geotechnical software tool that we have, like Plaxis, GeoStudio, Gint, and many other. So I'm educating the people, I'm giving the training, I'm also involved in the business development, marketing, and the sales for these software tools, not just for the India, but some neighboring country as well, like Pakistan, Bangladesh, Sri Lanka, and Nepal. So in this session, I'm trying to cover this topic, that is slope stability using numerical modeling. Okay, so I'll just take you through the outline of my presentation. So first of all, I'll give you some introduction about the slopes, what different types of slope, and then I'll take you through the different causes or the reasons behind the slope instability. And then I'll cover the different modes or the typical examples of slope failure, and we'll see the few mishappenings which happens in the India in last few years. That is nothing but the landslides in India. And we'll see the recent published codal guideline, or just a guideline by the Central Electricity Authority of India regarding the slope stability assessment, and that's particularly for the hydropower projects. We'll see that guideline, what that guideline talks about the slope stability. We'll see that in detail. And then I'll take you through the different methods of analysis. That is the main point of discussion. That is the methods of analysis for the slope stability projects. So as we know that there are two methods, one is the limit equilibrium and the second is the finite element analysis. So we'll see in a detail the assumptions, the limitations of each and every method. Okay, and then I'll take you through one demonstration. We'll try to solve one simple slope stability problem with the help of Praxis, means the finite element background, and then I'll solve the same numerical with the help of GeoStudio software. That means we are solving it by the limit equilibrium approach. Again, in that I'm choosing the Morgenstern price method, and just we'll see what is the difference in terms of the factor of safety when we are going with the FEA. What is the factor of safety, and when we are going with the limit equilibrium, what will be the change in the factor of safety, that we will see during that demonstration. And at the end, I'll try to cover one case study from the New Zealand, that is same means related to the stability analysis only. Of course, there are many case studies are there from India also, but now in this session, I'm covering that New Zealand case study. I'm just switching off my camera for better connectivity. Okay. So slopes, all we know that there are mainly two categories, or the two types are there, which we are categorizing. That is the natural, and the second is the artificial or a man-made kind of a slopes. So natural slopes are formed because of the several physical process that includes the plate tectonics, weathering, erosions of rock masses, sometimes the depositions of material, which forms a elevated kind of a natural structures that we call it as a slopes. Okay, and at the same time, there are some artificial or man-made slopes are also there, which we established to facilitate the different infrastructure projects, like for a road projects, for the railway embankments, for the earthen dam construction. And because of that, artificial slopes get generated. Okay, now coming to why there is necessity to find out the stability of these slopes. Okay, so again, the stability of slope is a critical, it having critical importance in not just in the geotechnical engineering, but in overall engineering. This stability analysis is again very important. So when we call a slope landslide, so when there is a movement of the soil material or the rock material along an inclined phase, we call it as a landslides. Okay, and it leads to several damages, including the infrastructure damages. Sometimes it may lead to the casualties. Okay, so that's why it is very important to determine the factor of safety for our critical slope, though it's a natural slope or the your natural slope or the man-made slope. There's stability analysis is again very important. Okay, so slope stability depends upon the capability of our slopes to withstand against gravitational force, means it's a self-weight. Okay, the self-weight of our soil or the rock material. In addition to that, sometimes some external loads are also there at the top of slopes. Maybe there is some construction, so that load is also there, which your slope must withstand against of that external load. And in addition to that, sometimes earthquake or some dynamic load also comes into the picture. So your slope must be withstand against all these different forces, like gravitational, some external forces, some earthquake or the dynamic loads. Okay, so this is all about the introduction about the slopes. Now, what are the different reasons or the causes which leads to the slope instability or the slope failure? So very first and the very common one is the increase in weight of the soil because of the saturation, because of the weighting. Okay, that is the main predominant reason behind many slope instability. Added external loads, as I just mentioned, some external loads at the top of your slopes may cause the slope instability. Sometimes the steepen slopes either by excavation activity or because of the erosion. That also one of the reason. Shock loads, vibrations, earthquakes, that dynamic loads also sometimes trigger our slope instability. Increase in moisture content, and in some regions the freezing and thawing action is also responsible for causing the slope instability. Now I'll just show you some typical modes of failure and some types, I can say, for a slope failure. And this is suggested by the Vons in the 1978. So the very first type of slope failure, which happens mainly with the rocky material, that is the faults, where you can observe simply downward movement of a rocky material. You can see that simply our rock material get detached from its parent rock. Okay, and in the case of falls, that movement is in a linear pattern. So you can see this rock fall in the figure 1A, and this is the actual example from the Spain, that is the rock fall. Now coming toward the second mode of failure, that is the topples. So it is similar to that of faults only. Okay, our rocks get detached from its parent rock, but along with the linear motion, sometimes the rotational motion is also there for our detached rock material. Okay, so you can see this is the example from the Colorado, USA. That is about the topple kind of a failure, where your rocky materials get detached from its parent rock, and that detached material, along with the translation motion, there is rotational motion is also there for the detached rocky material. Now regarding the slide, this is another modes of failure. Okay, and it is mainly because of when the applied shear stresses is more than the shear strength of our soil or the rock. Okay, and this leads to a shear failure. Okay, you can see that. Again, that slides are of two types. One is the rotational kind of a slide, which you can see in this figure 3, and there may be a translation slide, simply downward movement of this soil material. So you can see the translation rotational kind of a failure in this figure 4, and this is the example from the England, which happens in the 1993. And this is the translational kind of a slide, the translation slide failure. And this is the example from the Japan. And the reason behind it is the seismic activity, earthquake is responsible for this kind of a slide failure or the landslide failure. And this is the case from the year 2016. Further, you can see this is another mode of failure, that is a lateral spread, and it is mainly because of the liquefaction, and happens in the case of saturated soils. Because of this shaking or because of the earthquake, this shear strength get completely lost for a saturated soil, and this kind of a thing happen. So you can see this is the lateral spread happens in the Pakistan. Okay, and you can see there is a complete damage to this road or this highway. Another mode of failure is the flows. Okay, so so the failures which we cannot categorize in the earlier 4 category, we categorize them in the flow category. So what will be the flow kind of a failure? You can see that simple your soil material or the rock material, they flows along a inclined path. Okay, so you can see the debris flows or the debris avalanche. These are the few example of flow kind of a failure. Now we just discussed the different modes of failure, and now coming to our India. So there are a lot of examples that this slopes get failed. Okay, because of the several reasons. So these are the few news cutout which I have taken about the mishappenings or the landslide which happened throughout the India. So this is the case from the Kerala. From the year 2022, you can see that this road completely get blocked because of this landslide. It happens. This is another example from the Kerala itself. You can see that massive transnational kind of a sliding is happening along this region. Whole soil material, it's completely washed out. This is another from the northern part of India. Okay, almost 46 get killed because of this mishappening, because of this landslide. This is another photograph from the Himalayan region, over 50 killed again in that, and the rain is the factor which triggered this kind of a failure. This is another case from the Maharashtra. This is another photograph from the landslide damages. This road, you can see that road, portion of the road is completely get washed out. Okay. This is another example. You can see that rock particles get detached from the parent rock, and they are on now and on the road surface. And this is again the example from the Himalaya. And this is another case study, another in news from the Maharashtra. Okay, you can see the 12 killed in the landslide after heavy rain, and I guess this is the case from the from the Pune region. This is the example from the Sikkim. So, so many things, so many this kind of a landslide happening on every year in India, not in the Himalaya region, but the other parts of country as well, like in the Kerala, in the Maharashtra. Okay. So, is there any guideline available? Is there any suggestive measures are there to avoid this kind of a mishappening? So, recently, the Central Electricity Authority of India they have published one guideline, and in that they have clearly mentioned what we need to do to avoid this kind of a mishappenings. But this guideline is applicable for only for the hydropower project, because this is given by the Central Electricity Authority of India. But in their guideline, they clearly mention, I just highlighted the portion which is important in this session. That is what they mention in this guideline. So project authority should carry out a numerical model studies of vulnerable slopes, which means that where is the critical slopes, using either a limit equilibrium approach, or you can use the finite element, or you can use the finite difference method to find out the factor of safety for that vulnerable slopes or the critical slope. And of course, the
Excuse me, sir.
yeah,
Screen is
hello.
not visible. Screen is not visible. There are multiple screens that have been shared.
Okay. Again, I am sharing my screen. I guess it is screen, and again, I am sharing. Now my screen is visible.
Yes, sir. Thank you.
Yes,
Okay.
yes.
Okay. 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 So these guidelines are clearly indicating the role of software tool or the different numerical techniques to find out the factor of safety for a critical slopes. Of course, the input data is again important in this case. You need to carry out a in-situ test, some laboratory test to give the proper input data so that we can get the appropriate factor of safety for our critical slopes. Now, coming towards the main point of discussion, that is the methods of slope stability analysis. So I just distinguished the slope stability analysis methods into two. One is the limit equilibrium approach, and the second one is the numerical method of analysis. Again, in the numerical method of analysis, there is a continuum modeling technique, discontinuum, and the hybrid couple modeling. Okay, and in the limit equilibrium, which is very common in the case of factor of safety determination for slopes. Again, in that, there are a lot of methods. There is a Swedish frame, a Swedish circle method is there, ordinary method of slice, then the modified Bischoff's method, Lorimer's method, Spencer's, and the Sharma method. Now I will see the limitations and the advantages of each and every method. So now coming to the limit equilibrium analysis, as I mentioned, it is the most common and the widely used slope stability method. But there are a few assumptions are there behind this limit equilibrium analysis. So what are those? Let's try to understand those. So these equations, this type of analysis is based on the assumption that the slope is on the verge of failure and that the forces acting on the potential failure surface are in equilibrium. Okay, so this is the very fundamental assumption is there behind this limit equilibrium analysis. Okay, and as I mentioned, there are a lot of different methods. Okay, different methods of slices like the Fellenius method, Bischoff, Spencer, Morgenstern price methods are there, in which we divide our slopes into either vertical slices or sometimes in the horizontal slices. Okay, and what we are doing in all this method, we are trying to find out the horizontal forces, vertical forces, even the interslices forces for each and every slice, and finally we try to find out the factor of safety based on some equation. We'll try to cover that equation in the upcoming slides. Another limitation of limit equilibrium analysis is that, of course, it is very fast. It is compatible with many geotechnical software. Okay, and relatively very simple, of course, this limit equilibrium method of analysis. But sometimes when we are going with the limit equilibrium analysis, it neglects the effect of pore water pressure. I'm saying in some cases, or in some with some software tools. Okay, and also it neglects the soil deformation analysis and the stress distribution. These things are get neglected in many of the geotechnical software tools when we are going with the limit equilibrium approach. Okay, so yeah. Now, let's try to understand the different methods, the assumptions behind them, the equations that we use, and what is the probable slip surface that we assume for every method. Of course, as we know, the slip surface or the failure pattern is not completely circular, or it is not completely linear. Okay, it can be of any shape. But for simplicity in the analysis, these methods assume that slip surface or the failure surface may be circular or maybe of any other shape, or some method they are not assuming anything. Okay, so the very first method, that is the ordinary method of slice, which published this method published in the 1936. And the very fundamental assumption in this method is that the resultant of side forces is parallel to the base of the slice, which is not true in every case. Okay, because our resultant is not parallel to the base of every slice. Okay, it may be off horizontal, it may be little inclined. Okay, but they are assuming this thing to make the simplicity in their analysis. And the equation used in this to get the factor of safety is the overall moment. Okay, so the horizontal forces, vertical forces, that things they are neglecting in the ordinary method of slices. So this is the, I can say, the limitation of this very old method. And then the the assumption behind the Bishop's method, which published in the 1955, is the resultant of the side forces is a horizontal. This is this is not true in every case. Okay, and the equation that they use is the overall moment and the vertical forces. Again, the horizontal forces, that thing is missing in the equation. Okay, and the slip pattern or the failure pattern that assumed in the Bishop method is again circular. That is again not true in the real scenario. Similarly, for the Janbu, Morgenstern, Price, Spencer, and this Samani and the Medani, I have mentioned their assumptions and the equation used, and what is the slip surface that they assume in their analysis that I have mentioned over here. So not every method is accurate from the field point of view, but yeah, of course, with approximate, we get some values. Similarly, I have mentioned assumptions for the other methods for the Spencer, Morgenstern, Friedland, and Cran, crops of engineer, and the Sharma. So their assumptions I have mentioned over here. Okay, so now I'm just moving ahead because I need to cover a lot of part, the case study as well as the demonstration. Now coming toward the finite element analysis. Okay, so this is again more advanced and the sophisticated slope stability analysis method. Okay, of course, it also has some limitation, which I'll cover in the upcoming slides. This finite element analysis is based, it uses some equations of equilibrium, and it also uses a constitutive laws for a soil material. So constitutive laws means our regular more column material model is used to determine the factor of safety to solve this numerical equations of equilibrium. Okay. Of course, the add-on in the finite element analysis is that you can go with either plane strain approach, or you can go with the axisymmetric approach, or you can also go with the three-dimensional approach to create your slope geometry and the boundary condition. So I can say this is the add-on over a limit equilibrium approach. Okay, of course, we can do many of the things with the limit equilibrium approach also, like plane strain, axisymmetric, and the 3D. And another advantages of this finite element analysis is that we can able to consider the effect of pore water pressure in our analysis. We can also able to capture the soil deformations and the stress distribution in our stopy area. So that is, I can say, the some add-on over a limit equilibrium in the case of finite element method. And along with that, we can also able to simulate the different stages of loading. We can do a loading, unloading, or we can able to perform a consolidation analysis. Okay, also we can do a stage-wise construction analysis, and we can find out the factor of safety for our critical slopes. Okay, so this is, I can say, the add-on over a limit equilibrium approach. And Further, but of course, when if you want to do the consolidation and the loading and unloading thing, you need a precise data, precise input data. Of course, along with that, you need a good computational time and the expertise to analyze those results. Okay, when you are going with the stage-wise construction analysis for our critical slopes. Now, what is the mechanics or what is the mathematics behind the finite element analysis? Let's try to understand that, because we just run the software and we got the factor of safety, but many of the times people don't know how the Plaxis or this software tool that it calculate that factor of safety, okay, for our slopes. So the phi psi reduction method we are using in the finite element approach. Okay, so what is this phi psi reduction method basically? So factor of safety is calculated. It is equals to the available soil strength divided by the mobilized soil strength. So what is the meaning of this available and the mobilized soil strength? So uh, initially we are giving some input to our soil material or our rock material. We are giving that in terms of the C and phi value, cohesion and angle of internal friction. So what software doing? It applies some out of balance force. Okay, it means we are actually applying some shear strain on our structure, and we're trying to make it fail. Okay, so during that process, what software doing? Software continuously decreasing the shear strength C and phi value. Okay, and it checking where it get fail against of that applied shear stress. And so till the decreased value, so that reduced value we are considering at the bottom side, that is the mobilized soil strength, and the input data is at the top, that is available soil strength. So we are taking the ratio of that two things, and by that we are calculating the factor of safety. So summation of MSF is nothing but the factor of safety that we are calculating in that matter. Okay, again, this equation that I have mentioned over here, okay, it is applicable only when you are using the Mohr Coulomb material model for your soil or your rock. Okay, but when you're going with the Hooke-Brown kind of a material model, in that case this equation is not applicable. So for that case, which equation is applicable? I suggest you to refer a Plaxis reference manual, or you just Google, you will get that equation for finding the factor of safety when you're going with the Hooke-Brown material model. This equation is applicable only when you're going with the simple Mohr Coulomb failure criterion. Now coming toward the some limitation, I'm not saying limitation, but when you carried out some safety analysis with the Plaxis or any other software, you notice for that safety calculation, you have noticed a lot of very huge deformation. You can see for this particular example, you can see the dimension is 0 to 12 meters, something like this. Till here it is 28 meter, and this is 40 meter. Okay, so the total extreme boundary is from 0 to 40 meter only. But still, you can see the deformation that we reach in the safety analysis is the 35.2 10 to the power of -3 meters. So very huge deformation. So basically, this kind of a deformation in the safety analysis particularly, it does not have any physical meaning. Then how this value, from where this value comes? So that information I have mentioned over here. So as I mentioned, what we are doing in the psi-phi reduction method or phi psi reduction method, we are introducing one out of balance force in our model. Okay, and this out of balance will solve by calculation kernel, which will result in the deformation, and that deformation you are able to see over here. And this additional displacement that are generated do not have any physical meaning. Okay, we are applying some here software. What software is doing when we are running the safety analysis? Software is applying some shear stresses, out of balance forces, and it's trying to make this slope failure. Okay, and to till the reach to that failure, how much deformation is around, that information is mentioned over, but it is not having any physical meaning. Okay, our interest is here is the only factor of safety. Okay, the safety factor that calculated in this particular phase. I'll cover this part in detail during the product demonstration. So I just wanted to cover that this deformation does not have any physical meaning when you are checking the factor of safety or the safety analysis phase. Okay. Now, what are the advantages of finite element analysis? So I just summarized few advantages here. So of course, no assumptions need to be made in advance about the shape or the failure pattern, because if you remember in the different limit equilibrium approaches, we are when we are going with the ordinary method of slice. In that case, the mode of failure is always circular. So that is the assumption. So, but in the case of finite element analysis, such assumption is not there. So that is one advantages. Second, the failure occurs naturally through the zone within the soil mass in which the soil shear strength is unable to sustain the applied shear stress, which I mentioned over here in this last slide. We are applying some out of balance force. It means we are introducing some shear stresses inside our material model, and the failure zone or this failure get developed through a zone of weakness, okay, where your shear strength is low. Through that, this failure pattern get developed. Third assumption, the slice. Since there is no concept of slice in the FA approach, there is no need for assumption about slice forces. Okay, so of course here in the finite element analysis, we are not dividing our slopes into a horizontal slices or a vertical slices. So inter-slices forces, that thing is completely we are avoiding in this one. Then the fourth advantage is the FEM preserve a global equilibrium until failure is reached. The fifth advantage, if realistic soil compressibility data are available, means your Poisson's ratio, your density value, modulus of elasticity, the FE solution will give up information about the deformation at working stress level. So you can also able to get the deformations value, displacement values, if you are having the precise data in terms of the compressibility. And the last one, the FEM is able to monitor the progressive failure up to and including overall shear failure. So these are the few advantages I have mentioned over here over a LEM. But as I mentioned, some limitations are also there for our finite element method. So for the determination of factor of safety, in the case of finite element, we are using the strength reduction method, that is a phi-psi reduction method. Of course, it is a very powerful technique to get the critical slip surface or critical failure surface. But many of the times, our point of interest is not just a critical surface. We need a factor of safety at some other locations apart from a critical failure zone. Okay. So, however, there are some circumstances, some situation where which more information is required than just most critical slip surface, or when the critical slip surface is of minor importance. So, what are those circumstances? What are those situations where, apart from the critical slip surface, we need to see the factor of safety at some other locations? So, I just summarized few situations, some instances where apart from the critical or the global factor of safety, we need some factor of safety for the other locations. So first example, for a large dam, okay, both global stability as well as the stability of slope section in between the berms must be determined. Okay, so I'll try to cover with this image. Yeah. So you can see in this figure, this is a upstream side of my my dam, and this is the berm that we have given over here, and this is the downstream face you can see over here. So with the Plaxis or with the finite element approach, we are able to get only this kind of a critical surface, a critical failure surface over here. But if my point of interest is this location, then I'm not able to get this factor of safety for this location. That is the limitation of finite element analysis. Also, if I am interested in the upstream side, what is the factor of safety because of the drawdown actions or the full water reservoir level? What is the factor of safety? If I want to check that, I'm not getting that data because the critical zone is lies over here. So software gives me this value only. So this is one example. Okay. Then just I'm coming back. Okay. Then another situation for a road projects in the mountain, both the stability of the hillside above and below the road cut must be determined. Okay. So because the landslide or the failure happened from the above side, or maybe there may be washing out of road surface from the bottom side. So we need to check the factor of safety on the above and below of my road portion. Okay, so that is another scenario where the finite element analysis is lacking. Okay. So these are the few instances where our finite element approach has some limitations because we are able to get only the critical failure surface, critical failure with the finite element analysis. So in such a situation, you need to go with the limit equilibrium approach because in the limit equilibrium, you can able to set where you wanted to find out the factor of safety. You can just set this portion. Okay, if your interest is this portion only, just set as an input parameter, give the entry and exit point in the software. You will get the factor of safety for this region only. Okay, so that flexibility we have in the case of limit equilibrium softwares or the limit equilibrium approach. So I'm just concluding the theoretical part that we have discussed till now. Okay, still the actual demonstration and the case study still remain. So just be with me. So as I mentioned, in the case of finite element approach, the factor of safety emerges naturally without the user having to commit a particular form of failure mechanism. So in the finite element approach, we did not give the uh, prior failure pattern. It's a circular or it can be a linear. That prior failure pattern we did not need to give in the case of finite element. Further, there is no need to specify a range of trial surfaces. In the case of limit equilibrium software, we need to give the ranges of trial surfaces, 1,000, 100, like that. So that thing is not here with the finite element approach. And also, there is no concept of slicing in the FE approach, which we discussed. And so the assumptions about the slide forces or the slice forces, we are neglecting that part in the FE approach. So that is the good thing with the FE analysis. Now I'm moving with one simple Plaxis example, which gives you the more idea that how the factor of safety get changes when we are dealing with when we are going with the finite element approach and when we are going with the limit equilibrium approach. So I'll just try to show you that difference. So I have already made this example. I have already run this problem. Okay. So, but just for your understanding, I'll show you the properties of the soil that I have taken. Just make me clear, my screen is visible to everyone and I'm audible. Just give me a confirmation.
Yes, sir.
Okay, thank you.
Yes, sir. It's okay.
Okay, thank you. So here I have, for a simplicity of understanding, I have taken very simple example of a slope. Okay, so I have considered the two soil layers. So I just given the name as a lower layer and the upper layer. For your understanding, I'll just show you the properties for one layer. So I'm just showing what the property that I have taken for the lower layer. So the density values like this, unit weight value 17 and 18 kilonewton per meter cube. And then of course, the Motil model that I have used is the Moore Coulomb model. So 5-psi reduction method is applicable in this case. Now coming to the mechanical properties, the modulus value you can see over here is the 15,000 kilonewton per meter square. Poisson ratio is 0.25. C value is 4 kP and the phi value is 20 degree. I assume in the for the lower layer material. Okay, so likewise I created the upper layer also. Just coming back to the stage construction. So you can see here, I run the two different phases. One is the deformation phase and the second one is the factor of safety. So my main point of interest is to see the factor of safety for this particular slope and just see the geometry as well. So the top width is the 10 meter that I have considered. This incline phase is almost 20 meter. Okay, right now I'm not able to get how much angle for this slope, maybe around 30 to 40 degrees, like that. Okay, so this, you can see these phases that they are already run. So I'm now just moving toward the output. So how much factor of safety is there for this kind of a geometry for this kind of a slope. So I hope you are able to see the output. So I'm just showing you the deformation, how the failure get developed. And I'm just to say going to the total displacement, you can see this failure will happen like this. But if you see the displacement values, so they are almost 800 meter. Okay. So of course, as I mentioned, this is not having a physical meaning because right now we are checking the safety analysis. We are checking the safety analysis over here. But when I'm shifting toward the deformation phase from this drop-down menu, okay, so you can see the deformation is just 1.16 10 to the power of minus 3, means 1.16 mm. Okay, so again in that I'm shifting toward the horizontal displacement. So these are the horizontal displacement value. But the main point of discussion in this is the factor of safety value. So how to see the factor of safety value? So for that, just go to the project and in that the calculation information. And our target is to see the summation of MSS, that is the factor of safety, and now it is 1.135. Just give me a second. The factor of safety in this is the 1.135. Okay, so this is the finite element approach that we have adopted to get the factor of safety. Now I'm trying to solve the same problem with the same input data, same geometry with the limited approach. And in that, again, I'm going to use the Morgenstern price method. And let's see how much factor of safety that we'll get. So with the finite element, we got factor of safety around, let me check again. It is 1.135. Okay, now let's try to solve the same problem. I'm exporting this file in the GeoStudio software. And where we'll adopt a limit equilibrium approach, that is the Morgenstern price method, to solve the same problem. It will take some time to import this file in the GeoStudio. Just give me a moment. Okay. So now we have imported our geometry from Plaxis to GeoStudio. Okay, so you can upper layer and the lower layer and the other things. So I'll quickly show you the method of analysis that we are choosing over here for this particular problem. So I'm going to use the Morgenstern price method for this problem. And you can see the slip surface that I'm assuming direction of movement is from left to right. And entry and exit point I'm using for the further things. Okay, so now I'm giving the entry and exit point. That is the input that we need to give in the software. So I'm suggesting this range for a entry point. I'm suggesting approximately this range for a exit point. Okay, now I'm just clicking on the start button to solve this program. It will take some time to get the output. Yeah, now it runs perfectly. So you can see that this critical slopes is divided into the vertical slices like this, which is one of the assumption in this, and the factor of safety that we got is a 1.16. If you remember, the factor of safety that we got with the Plaxis is 1.13, something like that. I'll just quickly open the output of FEM. So this is the failure pattern. And in the factor of safety, you can see the factor of safety is 1.135. And in GeoStudio with the Morgenstern price method, we got the factor of safety 1.16. But again, it may be because the model is quite simpler. That's why we get the near about similar result. But if the geometry get changed, even our entry and exit point get changed, location get changed, this factor of safety get changed accordingly. But I just wanted to show you that there's not much big difference if your geometry, the material input data, if they are more or less same. Okay, though there are a lot of assumptions are there behind the limit equilibrium approach, but still we are getting approximately same result. Okay, but of course there are some many informations are there. If you are changing here and there, you will get a difference in the result. Okay. Okay, that's about the this a problem. Now I'll go toward the one simple case study from the New Zealand, where that is a road construction projects. So I'll just quickly show you the problem. So this problem is already run. So you can see, I just quickly discuss the geometry and the soil layer and the sequence of construction. So you can see this is the top layer of that slope, and this is the bottom layer of soil. Sorry. And the target is to construct a road at this location. Okay, so the road of width is of course is going beyond the top layer of soil. So of course we need to refill this portion to accommodate the total width of the road. Okay, so for that purpose, we first of all we excavated this portion of the soil. Okay, and then I added one more phase to create a fill at this location to accommodate the total width of the road. And then in the next phase, I constructed a road as a plate element I have used over here. Okay, and then after constructing a road surface, I applied the traffic load. You can see that the load now activated in that another phase. After that, after constructing the road and the constructing the traffic load, I conducted the safety analysis, factor of safety for this portion. Okay, and again, I consider very extreme situation, extreme condition. Now you can see that now in this phase, the water level is like somewhere here. And in the another case, what I did simply I raising this water level. So just I'm simulating the rainfall condition or the saturated soil condition, and wanted to check what is the factor of safety, how much factor of safety get reduced because of this increase in water level. So that's why after this increase in water level condition, I again run the factor of safety analysis. And after they found that the factor of safety is not as per the requirement, so that's why they provide a soil nail. You can see that after running this factor of safety, I am going to the top soil nail level, that phase where we just activated this single soil nail in this failure pattern. And then again, we check the factor of safety. We need to check how much factor of safety get improved with one single soil nail activation. And after that, we also activated the remaining 2 soil nails over here. So now let's come to the output. Now I'm showing you the output for our natural slope, no excavation, no construction, no soil nailing, how much factor of safety was there before the construction. So I run that analysis as well. I'll just quickly show you the factor of safety for that one. So I'll show you the total displacement. So failure pattern is likely to be this one. Okay. And as again, I'm saying, when you're checking the factor of safety that phase, don't get panic when you're seeing this kind of a deformation. They are not having any physical meaning. Okay. Now coming toward the factor of safety, I'm again going toward the project and see the calculation information. So how much factor of safety is there for the natural slope? So for natural condition, the factor of safety is 1.25. Okay. So this is the factor of safety. And now I'm moving toward the another phases. Okay, so I run another factor of safety. Okay, that is after whole construction of road and the filling of this extra soil over here, applying the traffic load, and let's see the how much factor of safety is there after constructing a road. So again, I'm going towards the project and the calculation information. So now this time you can see the factor of safety is 1.48. Okay. Now there may be a question in your mind. Prior to road construction, the factor of safety was 1.25, and after the road construction, why the factor of safety get improved to 1.48? So that is mainly due to we are constructing this reinforced field over here, this improved property soil layer over here to accommodate the road width, and because of that, the factor of safety it get increased little bit because of this feeling area, this good quality soil over here. But still, the factor of safety is 1.48, not more than 1.5. So that's why what they have done, they applied a single soil nail. But prior to that, I wanted to show you what is the effect of water or on the factor of safety analysis. Okay, so till now the water level is at this location. Now I'm shifting this water level to little upward like this. Now you can see the water level is like this, and let's check how much factor of safety is there when the water level get increased. Means we are just simulating the rainfall effect, or you can say the saturation effect. And let's take the factor of safety for this case again, project, and I'm going to the calculation information. So you can see that the factor of safety now reduced to 1.42. So before increasing the water level, the factor of safety was 1.48. Now it drops to 1.42 because of the increase in water level, or you can say the pore water pressure effect comes into the picture. Now let's see how much factor of safety get improved when we apply one top soil nail at this location. Okay, so I run the factor of safety analysis just after that. You can see that the failure pattern now shifting from this side to the top side. Okay, and now whatever the factor of safety that we are checking in this particular phase is the factor of safety for this critical slope, not for this bottom side of my road. But let's check. I'm going to the project in the calculation information. The factor of safety for this top portion is now 1.75. So now I can say this is the limitation of this finite element analysis, that we are not able to check the factor of safety for this region. Okay, so So with one single soil nail, the factor of safety is reaches to 1.75, and we have added two more soil nail over here. But I guess I haven't run the factor of safety after that one. Okay, sorry, I haven't done the factor of safety analysis after adding two more soil nail. Okay. Okay, so this is the failure pattern. I'll just show you the with single soil nail. Yeah. So you can see that this may be the probable failure surface for the top zone, and the bottom portion get secured because of this one single soil nail. But prior to that soil nails, if we check the failure pattern, it was lying somewhere here. Okay, like this. But because of addition of one single soil nail, this failure pattern, it's shifting from this to the top area. Again, the inclination of the soil nail, its length, they determine after doing so many trial and error, and then they fix the angle of soil nail and the properties, the diameter, length, and other input parameters for that one. Okay, so that's all from my end. If we are having any questions, any doubt, please ask me.
First of all, thank you, Dr. Deshmukh. That was a very beautiful lecture. I mean, you started from the very basics, because we have so many of the students joining us. So they always want that some speaker come in, you should always start with the basics. So I think you explained it very well, how the modeling is taking place and what are the parameters, how they should be kept in place. Before we could start with the question answer session, just an important announcement to you that we, along with the Civil Engineering Department, JUIT, are organizing an international conference on civil materials and environment for sustainability, which is set to occur on 4th and 5th of October. So we have mentioned the link in the chat box. Please go through the link, and anyone, if interested, can submit his or her abstract into that. So again, I'd like to thank the speaker first, and then kindly ask him if we can go to the question answer, please.
Okay.
So let me read the questions. So the first question is from Nikhil Kumar Pandey. Can we apply the Mohr-Coulomb model for rock slopes as well, at least for soft rocks?
Okay. Many softwares are considering the Mohr-Coulomb model for the slopes. Plaxis does not consider it, in my knowledge. Mohr-Coulomb for rock. Okay. Through, in my opinion, that would be not accurate. What do you think? Okay. Yeah. So to model the rock, yes, of course, we can able to use Mohr-Coulomb model. But what I suggested, when you're doing a slope stability kind of a analysis, okay, you can perform that one. You can assume your rock material as a Mohr-Coulomb model, and you can perform the slope stability analysis. Okay, but what I'm saying, when you're using Hooke-Brown material model for your modeling your rock, in that case, that phi-psi reduction method or that strength reduction method is not applicable. That was my suggestion, or that was the thing. So of course, you can model your rock with the simple Mohr-Coulomb models. It is possible.
Okay. Another question is from Zafina. Sir, why are you simulating road as a plate element, and what will be the property of such a plate?
Okay. So this is, first of all, this is not my case study. This is the case study from the New Zealand region. Of course, you can use a simple linear elastic material for modeling the road, and you just give the higher E value, like the 10,000 megapascal, something like, which is given there in the IST 37. Okay, give that one and you can simulate. Okay, if you are asking me why they use the plate element in that case, maybe to check the few stresses and other things. I'm not sure about it. Now coming toward the property, which property that I have used, I'll quickly show you. I'm just sharing my screen so that you will get the properties of that one. I'm just sharing. Yeah, coming towards the structure, and you're asking about this plate element, its property. So of course we need to give the axial stiffness and the flexural stiffness for that one. So I'm just going to the plate and the road surface. Just I'm going to the edit, and you can see these are the EA and EI values which they have taken in their analysis. Okay. So in that case, you can simply take the modulus of elasticity as per your bituminous metal or as per your pavement material, and simply multiply with its cross-sectional area and the moment of inertia, so that you can simulate your road surface with the help of plate element as well. Or not, if you do not want to go with this approach, simply make a simple layer of your bitumen, of your pavement thickness, give the property of E as per your pavement material, whatever it is, and go for the further analysis. I hope I clarify your doubt.
Right, sir. I think so. That would have been clarified. There's another question from sort of this Pandey G. Can we use Python-based codes to generate slope models in Plaxis if there are a number of problems to solve?
Yes, of course, of course. So Plaxis supports you for this Python scripting. So that feature is available. So you need to generate your code first, and just need to change the parametric change, like C5 parameter or the geometric parameter, whatever you wanted to change, and just run your that Python code. Yes. So the answer is yes. You can able to perform this Python-based scriptings, and you can perform your slope models.
Right. And the question is from Mr. Amanpreet Tangri. Sir, could you mention various reasons for difference in results of physical modeling and numerical modeling for slope stability?
There are a lot of reasons when you are doing the physical modeling, and if you wanted to validate the same with the numerical, because there may be scale effect is there in the physical modeling, which may not be we consider in the numerical modeling. So there are not one reason, there are a lot of reasons are there when you are not getting the exact result. But when you are doing everything properly, you will get near about results. But of course, you will not get the same result that you obtain with the physical or the experimental models.
Yeah, I think heterogeneity of the soil in the real model and the model is also a big difference.
Right, right. So there are so many reasons that make the difference between the results.
Yeah, another question is from Rasimiranjan. How to validate slope stability problem experimentally?
So if you wanted to do the slope stability, if you go our fundamental book, our UG books, there are a lot of slope stability problems are there. Okay, you can use any of the methods, steady circle method, friction circle method, to get the approximate results, and you can check your experimental result with that one. So Bishop circle method is there, steady circle methods are there. So many methods are there with which you can validate your experimental problem.
Right. Next question is from Pankaj Gupta ji. I want to know that if we can develop pi curve for piles used to stabilize the slope during dynamic loading in Plaxis.
I want to know that if we can develop, yes, we can able to develop the load versus lateral deformation kind of a curve for your piles that you want to do. Yes, it is possible. And against of the dynamic, yes, it is possible.
Right. Next question is from Shweta ji. Sir, as you have said that we can't get factor of safety for lower portion of the slope, so can we use FELA for calculating factor of safety for upper as well as lower portion, but continue our study further in Plaxis software? I think it's about the side-by-side application of FELA, which is also a application software along with the Plaxis.
Yeah, along with the Plaxis, you can able to do, but sir, as you said, we can't get the factor of safety of lower portion of the slopes. So we can use FELA for calculation for FOS for upper as well as lower portion, but continue. Sorry, still unclear for me. But for half portion, I understood, sir. We can't get the factor of safety for lower portion of slopes, so we can use FELA for calculating. Okay, you can use, of course. And yeah, you can remaining thing you can do with the Plaxis, right?
Right. Next question is from Professor Bashir Ahmed ji. It was very informative and well explained presentation. Thank you, sir. Thank you very much.
Thank you, sir.
Next question is from Pankaj ji. If we are analyzing the dam, which model is to be considered for riprap on upstream and rock toe on downstream?
Yes, so answer is yes, you can do that one. You need to just consider the improved property for your rock on the upstream side or the downstream where you wanted to provide this riprap, and just consider that fluctuation of water level also you can able to simulate, means rapid drawdown, side or drawdown. That condition also you are able to simulate with the Plaxis, and you can able to check the factor of safeties for that critical conditions with the help of Plaxis.
Okay. Now we do have a series of questions from Usman ji. So we'll take one by one. So question one is that while performing safety analysis in Plaxis, can the output results show the final soil parameter C and phi values reduced to calculate the factor of safety? And are the results of safety analysis of Plaxis 2D and 3D is same?
Okay, so coming to the first question, sorry, I'm. This is a really fantastic question. I haven't checked. Of course, it's a phi-side reduction method, so your question is very good. But sorry, I don't know, means whether really we are able to get that. How much the reduced C and how much the reduced pi value is there. So for my side, I'm really sorry, I don't know. And now you're asking, are
Excuse
the
me, sir.
result of safety analysis? Yeah, please,
Sir,
please.
from the formula that you have shared in the presentation,
Yeah.
that
Yes,
MSF
yes.
is equal to C by C reduced. So when we get the
Right.
factor of safety, for example, 1.5, we have to just divide it by the actual input that we have given to the Plaxis. So C reduced and phi reduced, we will obtain from that formula only.
Yeah, miss, we are back calculating basically. For example, we received a factor of safety 1.3 and the actual cohesion is, for example, 45 kPa. Just divide that 45 kPa by 1.35 factor of safety, you will get the C reduce. That's what you are saying, right?
Yes, sir. Yes, sir.
But actually, he's asking with the Plaxis, is there any provision in the Plaxis itself that we are? So your approach is also right, but from the Plaxis, if you're asking, I'm not able to see, is there any value? It is there. I'm just cross-checking if I have anything to show you. Uh, sorry, at this moment I can't. Okay, sorry. At this moment I can't able to see that one. And now I'm coming to the second part. Are the result of safety analysis of Plaxis 2D and the 3D is same? So again, I'm not able to comment on this because I haven't checked the same 2D model and just excluding in the 3D and checking its factor of safety. But it should be same. It should not be same, but it should be at least near about that factor of safety values when you are doing the same, but only the 2D and the 3D difference is there. And
Yeah,
there
I
is
think
another.
that's a very interesting question because whenever someone has to choose between a Plaxis 2D and 3D, people always are thinking about this question.
Right, but my suggestion is to go with 2D only when you are doing only safety analysis. So that is my suggestion.
Right. Adding to that, Dr. Deshmukh, can you please tell what are the additional things we get in Plaxis 3D?
It's same only. Only the third axis get introduced in this, but from the output point of view, from the calculation point of view, everything remains same.
All right.
Yeah.
Okay. Coming to his next question regarding the deformation in safety analysis, you told that it is not physical. How to calculate the deformation then in the main Plaxis analysis?
Yeah. Okay. Again, I'm sharing my screen, so it will. So for that, I already performed. If you remember, I performed two different analysis. Okay, for that project, where I run first the deformation. Sorry, it is running somewhere. So I run two different phases. One is the deformation phase, and the second is the safety phase. So in the deformation phase, whatever the result that we obtain is your deformation value only. I hope my screen is visible. You can see that. This is the
Yeah.
deformation phase I have run, and this is the factor of safety phase I have run. So if I click on the deformation, and for in detail, if you want to see, I'm going in the edit, and you can see the calculation type that I have selected is the plastic, means the deformation or the stress strain type of calculation only. So the output of this phase is nothing but the deformation. So you need to run the separate phase to check the deformation in the horizontal, in the vertical direction. Okay. So if I am going over here, so you can see the deformation value is almost 1.16 mm. Okay, for this case. So you need to run the separate phase to see the deformation values.
Right, right, right. Thank you, sir. Uh, there is another question from Pankaj Gupta ji. Sir, please can you demonstrate how can we develop the PY curve in Plaxis?
Okay, I need to conduct another separate session in this one because I need to model actual pile and run the model, and then we need to select the nodes on every point so that we can able to develop a curve for that.
Definitely. I think when we'll be organizing the next part of this series, we'll definitely be calling you, sir, again, and we'll be doing some another demonstrations on the finite element analysis.
Right, right. I just would like to mention one thing over here. So we are having one webinar. I'm just sharing my screen, and that is on rainfall induced slope stability using Plaxis. So that is this is the part one, and in the part two we are trying to simulate the same thing with the GeoStudio software. Okay, so this is going to be happen in the on May 16. Okay, so if you are interested, and this is on Plaxis 3D. So here we are considering the Plaxis 3D for rainfall induced slope stability analysis. So if you are interested, I'm just sharing this link. If any one of you are interested, just register and participate in that one.
That is quite interesting. Even we being in Himachal Pradesh are regularly witnessing such problems on the slope stability. I think that will be beneficial for us as well. Sir, adding to that thing, I just wanted to know that many a times when we are like interested in the rainfall induced landslide problems, and especially when we have to design some retaining walls, etc., at some failure slopes, then like the water table is actually very deep, and still if someone wants to like incorporate the effect of the water table, what can be done?
You mean to say if you effect of rainfall if you want to simulate?
Yeah.
So like in the earlier case study which I have shown, in that case what they did, they simply pore water pressure comes into the picture. So that approach you can adopt to simulate the rainfall effect. Just increase the water level and do the analysis.
All right, all right, all right. But the level of the water still needs to be decided. Is it okay to keep the water level at the slip surface, somewhere at the slip surface?
Yes, yes, it should be, and just make it till top level if it is possible, if the saturated soil is there. So just increase that level. So again, that is that we need to do a lot of trial and error. Where should we need to set that at top water level? That is again, you need to do the trial and error process to find out the lowest factor of safety for our slopes.
Right, right, right. So let's take another question from Dr. Saurabh Rawat. How to converse the error of soil body collapses for slope stability problems? Is it a boundary condition issue? What value should one check to rectify this issue?
Yeah, so soil body collapse is a very common problem. Means those who are new with the Plaxis that they are facing, but when you are get expertise over the Plaxis, you will come to know why there is this kind of a messages appear. So there may be a couple of reasons behind it. Your input data may not be sufficient, means your E value is quite lower, C5 value is not sufficient. In that case, also Plaxis showing that your soil start collapsing. Okay, soil body collapsing. Sometimes your data is perfect, but the loadings are quite higher, so it will not reach to the summation of msef equals to 1. Means it will not reach to its 100% calculation. So that in that case also this kind of error comes. So you need to check two things. One is your property input data for your soil and the rock material, and the loading condition that you are considering. If both are okay, then I guess it needs to be get calculated. But in both the cases, means your input data it's lower than the loading applied, it gets failed. Okay.
Right. So there is a query from Kiranji: why Plaxis LE is not used?
Plaxis LE is also people are using, but Bentley recently acquired GeoStudio. Okay, and GeoStudio runs on the limit equilibrium approach, and Plaxis is also Bentley product, and Plaxis ELE is also there. So to avoid this confusion amongst the user, now Bentley itself now not promoting the Plaxis ELE, because we are already having separate ELE tool, that is the GeoStudio. So that is the strategic reason behind it. People are means we are not promoting ourselves, the Plaxis ELE. Plaxis ELE is still there. If you are checking our web store, Plaxis 2D Work Suite is there. That is the combination of Plaxis 2D Ultimate plus Plaxis ELE, and it is still there. We are still selling that tool, and people are using, but we are officially we are not promoting that one.
Right. There is another question from Nidhi. Soil testing options are also available in Plaxis after we give the material properties. Can you elaborate on its usage and application?
Yeah, soil testing feature is there, right? You rightly said. So, for example, you have given some E50 odometer and the EO unloading value, the modulus of elasticity value I'm saying, and at the same time, you have conducted some triaxial test for your soil material, and you have a curve for that. So you just simply import that curve in that soil test feature and back calculate your E values based on that input data, and just cross check the E50 E odometer or the modulus of elasticity that you have assumed is matching with the output that we collected from the soil test feature. So just to back calculation thing, this soil test feature is there. You need to import, you need to add the actual experimental curve in that one, and then back calculate the C5 value, the modulus of elasticity value for to just validate your input data.
Right. The next question is from Danny Juice. So what about the fully coupled flow deformation analysis for slope stability analysis under rainfall condition?
So what about the fully coupled flow deformation analysis? Yes, fully coupled flow deformation analysis we can able to perform with the Plaxis. It is possible. So there is a separate calculation tab is there. Just a second, I'll show you by my screen. I hope my screen is visible.
Yeah.
Okay, so in this calculation tab, you can see the fully coupled flow deformation type of analysis is there. So for your particular that phase, you need to select that one and then run the analysis. It is possible that feature, that kind of a calculation is there in the Plaxis.
Right. There are a lot of praises for your lecture, sir, and people are asking for the email IDs as well. So I'll request you to kindly share your email ID in the chat box.
No worries. I'm just writing it. I'm giving you my official email ID. You can reach out to me there. And you can also take
Right.
my. So I have given my both personal as well as official email. You can reach out to me if you're having any doubt, questions, or queries.
Right. So we have one contestant, Nimawat Ekta ji. You have raised your hand. Can you kindly unmute yourself and ask your question? Nimawat Ekta ji, can you hear us? Okay. In that case, we'll move on to another question from Nidhi ji. I tried to model a tunnel by excavating and introducing the linings, but I keep getting error 204. Slow convergence. How to solve this?
If you're asking me regarding the tunnel and particularly for this error 204, I don't know what is this 204. I need to check the reference manual for the Plaxis for this error code. But I'll suggest you just refer the reference manual for all this type of error. What is the solution or what you can do to avoid this kind of error? That thing is there in the Plaxis reference manual. So I'll suggest you to go and check the Plaxis reference manual for this one.
Right. Maybe if possible, you may contact the speaker later on. Now, another question is from Bipin Karki ji. Can GeoStudio perform liquefaction analysis?
Yeah, in the GeoStudio, there is one separate software, or you can say the part of GeoStudio only, that is a Quick W. So with the Quick W, you can able to perform. Quick W is nothing but you can perform a dynamic analysis or earthquake kind of analysis in that one. So with that Quick W, it is possible to perform the liquefaction analysis.
Okay. Musaib Najirji has asked for the stability analysis of a retaining wall. Can we use plane strain model?
Again, before commenting on this thing, I need to check whole geometry. So of course, yes, it is possible to go with the plane strain model for a retaining wall, but simply yes, you can go with the plane strain model for a retaining wall analysis, because the axisymmetry is not applicable in this case.
Right. And the question is from Aniket Desai ji: how to simulate slope stability under earthquake load using pseudo-static method or pseudo-dynamic method?
Yes, both the methods are applicable. You can perform the pseudo-static and the pseudo-dynamic method. Only thing is that from the calculation type, you need to select the dynamic calculation type, and then rest you need to give the input parameters, how much time if you want to allow your model for that earthquake or for that vibrations. So that thing you need to give as an input parameter in the calculation tab. So the calculation, simply you need to go with the dynamic and give the rest of the parameters, the timing and everything.
Right. Next question is from Dr. Saurav Rawat. How much error can we assume when using plate element for modeling reinforcement in slopes, since the interaction behavior will be significantly different from actual site conditions? What exactly the virtual thickness value is used for? Many reported literature states that it does not affect the interaction values.
Okay, so my suggestion is don't use plate element when you are modeling the reinforcement, for example, geogrid or any geosynthetic material like geotextile. So you go with the geogrid element. So that element is already there in the Plaxis. Use that one and use proper axial stiffness value, means it's tensile strength of your geosynthetic material and the interaction factor, that is R inter, strength reduction factor. So how to get that strength reduction factor? Again, I'll suggest you to conduct a pull out test or large direct shear box test and find out the interface value from that one, and use the geogrid element only to simulate your reinforcement elements in the slopes. That will give you the more accurate results than your plate elements. So my suggestion is don't go with the plate element, go with the simply geogrid element, which is already there in the Plaxis.
Right. And the question is from Sofiane. In Plaxis LE, there is probabilistic approach. My question is now, how about the GeoStudio? This is follow-up of the last question, I think, which she asked earlier. Yeah.
Okay, in Plaxis LE, there is probabilistic approach. And yeah, you can also able to perform this probabilistic approach with the GeoStudio. Go into the slope W. In the analysis type, you need to select that approach. That approach is there. You can do the same thing with the GeoStudio. It is possible, the GeoStudio.
Okay. Now I'll invite Abdul Salim Khanji to kindly unmute himself and ask his query.
Abdulji, hello.
Abdulji, you have raised your hand. Do you have a query?
I guess by mistake.
Okay. Any other participants who want to ask some question directly to the speaker can unmute themselves and ask the question, please.
Hello, sir.
Hi.
Sir, actually, what are the factor safety we got in any method, like finite element method, that 1.8, any factor of safety? How to validate experimental means we have to construct a slope in our laboratory, small scale slope. What are how to validate?
You are saying the result that we obtain with the software, how to validate those results, right?
Yeah.
Yeah. So if your geometry is simpler one, like a road embankment or geometry is simpler, in that case, I'll suggest you to perform a simple hand calculation by using Bishop method or the steady circle method. Okay, and check the factor of safety with that one, and then try to simulate the same problem in the software. In that way, you can simulate. If your geometry is simpler, I'm saying.
No, sir. Suppose we will apply some external loading. Suppose I will prepare a slope. Then I will apply some external loading. And in software, I found I got suppose one of the factor of safety. But in real case, how to get that factor of safety?
In real case, sorry, I'm not able to answer this one.
I think the problem that is defined is actually a reverse case. That usually we have a problem in physical and we define it in the software. Now
In the
he's asking
software,
that we are
in reverse.
yeah, having a problem in the software and we have to define it in the physical.
In that case, you need to use some field instruments like inclinometers and some other things to check how much deformation, how much inclination is happening with the time. But again, with the time dependent phenomena, it is quite difficult to see how the failure get happen with the time in the software. But this field instruments, you can able to check the deformations that are happening. Like you can use some field instruments like inclinometer, settlement gauges to check the actual behavior on field. That way also you can cross check your software results with the actual field results. But up to how much extent it is possible, I'm not able to comment on that one.
Right. So, sir, you have to do, in short, some physical modeling and including all the dynamic effects and everything.
Right.
So if there are any other questions from the participants, you can kindly unmute yourself and ask the question.
Hello, sir.
Yes.
Sir, actually, when we define the safety analysis, so whether the safety analysis will be performed only for the phase which is defined before that, or is it for all the phases that are defined before the safety analysis, safety phase?
Okay, so the safety analysis that you're running, it just prior to that one. For example, just sharing my screen to give you the clear idea. I'm just switching on to the another problem. So in that project, we run the factor of safety analysis at different stages. Okay, means prior to the road construction, then after the road construction. So I'll just. Okay, so you can see after initial phase, I run the stability prior to road construction, means before excavation and everything. So this factor of safety that we obtain in this second phase is for this initial phase only, means for this geometry only. Similarly, if I come to this factor of safety, which we run after the traffic load application, this factor of safety is just after the traffic load construction, but it also considers the effect of all these phases which we considered earlier, means the road excavation, then the construction of field, then the construction of road, traffic load, and then we run the factor of safety. So in short, this factor of safety considers the effect of all these prior conditions. Okay.
Okay, sir. And one more
It's not
question,
just
sir.
the
Actually,
factor of safety of,
yeah,
please tell.
yes, sir. And also there is an option of reset small displacements or small strain. So whether that will have the influence on calculating the factor of safety in the stability analysis?
Yes, so I'll suggest don't touch anything in the deformation control parameters when you're dealing with the factor of safety analysis. Okay, so that is my suggestion. Only thing is that just select the calculation type safety and run the analysis. Don't change any default parameters in this reset displacement to 0, reset displacement small strain to 0. When you need to use this one, when for example, this is the initial phase, and when you are shifting from initial to the first road excavation. Okay, so in this case, I'm considering this reset displacement to 0, reset small strain to 0. So what is the meaning of this? So I'm simply ignoring the deformation which happens in the initial phase condition. So in the initial phase, what we are doing, we are simulating the gravity loading, means self stress, self weight we are considering. Okay, the deformation because of the self weight. Of course, because of the self weight, some deformation is there, right, in the material, in the soil. That may be 1 mm, 2 mm, 100 mm, whatever it is. But in this phase, in the road excavation phase, my intention is to see the deformation because of the road excavation only. Okay, if I'm not selecting this reset displacement to 0, so whatever the deformation that I obtain in this phase is the accumulation of the deformation in the initial phase because of the self weight, because of the gravity loading, plus because of the excavation. So my intention is to see the deformation because of the road excavation. So that's why I'm considering the reset displacement to 0 over here. Okay, and in the case of factor of safety, you did not need to do anything with these parameters when you're doing with the safety analysis.
Okay, sir. And also, like, if we are doing some plastic analysis or fully coupled flow analysis, so there is an option of mentioning or specifying the time of the time interval. So that is in days. So whether that will have the effect on this plastic analysis, sir? If we keep it 0, even then it will analyze.
Yeah,
and if
time
we
in
mention
days.
some data there, that will also analyze. So whether that will have some influence.
This time in data is basically is important when you're performing the consolidation kind of analysis. In that case, this having a real importance. This time in days when you're performing the consolidation analysis. Yep.
Okay, sir. Thank you.
Okay, are there any more questions in the list? If no, your feedback link I have already shared in the chat box. Please go through that. The link will be opened 10 minutes after the closure of the lecture. So I think we are done with the questions, and Dr. Deshmukh, and we are highly thankful to you for deriving your precious time and coming on to this stage of IGS Shimla chapter.
Thank you for giving me this opportunity. I would like to thank you, Neeraj, for inviting me in this session, and also I would like to thank Jaypee University and the IGS Shimla chapter, and best of luck for all your future events.
Thank you, sir. It was very nice interacting with you. We'll surely be calling you again and again because you are a very good teacher as well, I think.
Yeah.
So,
Sure.
Dr. Ashok Kumar Gupta, if you can hear us. No. Dr. Ashish. No, I think both of them are not there. Okay. In that case, we announce the closure of the event now. The entire 5 days of the lecture series are announced to be over now. We congratulate all the participants for a very healthy participation throughout the lecture series, and will surely be joining you again in the next part of the series. So till then, goodbye, and thank you very much for joining. Those who have not filled the feedback form, the link will be open for the next 10 minutes. Thank you. Thank you very much.